Well, good morning, everyone. It is a sunny morning over here at MIT.nano, and it's great to have you join us. Thank you very much for being here with us. This morning, we have an absolute pleasure of welcoming Ahmad Zubair as the speaker of this next Nano Explorations talk. He will talk to us about challenges and opportunities for the next generation of power electronic devices. Ahmad is a postdoc at MIT working with Professor Thomas Palacios. He finished his PhD with Thomas and Millie Dresselhaus. And we very much look forward to hearing his talk. Before he starts, I will remind you that you should turn off your video and mute your sound if you haven't already done so. That will increase the bandwidth for the rest of us. If you have any questions, please feel free to send them in a chat and we'll make sure to read them off. Beyond that, you can, at the end of the talk, just raise your hand and I'll call on you and we can ask Ahmad any questions that you might have for him. At this point, I will ask Ahmad to take over.
Thank you, Vladimir, for the kind introduction. It's my great pleasure to be here today because we have been using MIT.nano facilities for all our work for many years, and it's a pleasure to present the work to the community. So in my talk today, first, I'll give a brief introduction about vertical GaN power FinFET and our recent work on GaN on silicon FinFET and a novel substrate replacement technology that we have recently developed. So first, I'll point everyone's attention to this well-used figure over the years to showing how the power density and the transistor count is changing in a microprocessor. I would like to particularly draw everyone's attention to this figure. The typical power level in a transistor microprocessor is about 100 watts. And now, if you want to look into the application space of power electronic devices, this is a figure from a traditional textbook from 2008. And we see that the application space of various power electronic devices have a much wider range than the microprocessor, expanding from 10 volt to 10,000 volt and from a few milliamps to 10,000 amps. And if we try to plot the power level of microprocessor, it just falls below here, which means the application space of power electronics in terms of voltage and current rating has a much wider range than any other electronic applications that we experience in our everyday life. And that's not all. Recently, there have been a lot of emerging application of power electronic devices. We have power electronics everywhere in our electric vehicles, the inverters, and the data centers. And the market for the power electronics has been exponentially increasing for last decade or so. And we expect it to increase in the same fashion, if not more, in future. However, the energy efficiency of the power electronic device is the key for a better future. Why? If you look at this plot here from the Lawrence Livermore National Laboratory, the total generated electricity in 2019 in the US, and bulk of it has been wasted through the inefficient use. And now by 2030, a significant part of the generated electricity is expected to flow through the power electronic devices. And as a result, we need to have our power electronic devices as efficient as possible because we do not want to lose our energies just because our power electronic devices were not efficient enough. So currently, the power electronics market is dominated by the silicon devices. On the left, I have a plot where I show the typical performance metrics of the power electronic devices. On the y-axis, we have the specific on resistance, which determines the switching loss of the device. We want every power electronic device to have as lower switching loss as possible, so which means we have to have a lowest R on RSP possible. And on the x-axis, we have the BV or breakdown voltage that determines the voltage handling capability of any power devices. Now, if you look at the silicon curve, it's somewhere here on the top left. But due to the excellent material properties of wider bandgap materials such as gallium nitride and silicon carbide, we can expect much higher performance improvement in power electronic devices. For example, we can expect more than 50 times improvement in the specific on resistance and more than 3,000 times improvement in the breakdown voltage if we move from silicon to gallium nitride, thanks to its wider bandgap and excellent transport and material properties. And in future, we also want to move to the lower right-hand corner with probably a new device architecture or technology. But for today's talk, I'll limit my discussion about gallium nitride. So the gallium nitride has been out there for a while, and almost all the companies now have their gallium nitride products in their roadmaps, and it's continuously expanding over the years. However, all these gallium nitride devices are based on a lateral geometry, or what we call high electron mobility transistors. On the left, I show a typical cross-section image of a high electron mobility transistor made of gallium nitride. Here we have a source and then the drain, and here we have the gate. And since there's a power device, to support the voltage handling capability, there is a ungated region, which is in power electronics technologies called the drift region. So this region is used to support the voltage handling capability. So although gallium nitride HEMTs or planar gallium nitride devices are everywhere, there are a few drawbacks that limits us to expanded capability into a large, much wider voltage range or current ratings. First of all, in a lateral geometry, it's difficult to increase the current rating because the current rating of the device depends on the total area of the transistor. Since the lateral geometry, everything is on the surface. If you want to increase the current rating, we have to make the devices really big. That affects the that also increases the device footprint. The same problem happens if we want to scale the voltage handling capability of the lateral devices. To increase the voltage handling capability of the lateral devices, we also need to increase this length of the drift region. Again, we get affected in terms of device footprint. The third is actually very important bottleneck is the heat generation capability. Since in the lateral geometry, the transport is happening at the near the interface. So, which means when we are flowing a really high current, all the heats are concentrated near the surface. And the bulk of the substrate is unused, and it's not helping to dissipate any of the heats. And the final problem of the lateral geometry is the non-uniform electric field. In a lateral geometry, electric field is concentrated at the edge of the gate, and that makes the reliability of these devices very challenging. Now, we can solve this problem by going vertical. The primary advantage of the vertical geometry would be we can achieve very high breakdown voltage without enlarging chip size, because now we can change that, we can increase the drift region, which is along the vertical direction, by just controlling the thickness of the epi layer instead of a device footprint. Also, we can play with the geometry and achieve much higher current capability without having to impact the footprint of the device. And vertical geometry also helps with the better distribution of the electric field and uniform heat generation. For example, if you look at the heat map of a vertical versus lateral power devices, as we can see here on the top, in the lateral devices, the heat is concentrated at the temperature of the device is very high near the surface, but in vertical devices, temperature is more evenly distributed throughout the substrate. And if you look at this plot, where in the x-axis we're showing the particular power density versus the temperature of the device, we can see that at the same power density, vertical devices offer much less temperature rise compared to the lateral counterparts. So all these advantages make us really excited to pursue the vertical devices in gallium nitride. And there have been a lot of work in the community on the vertical GaN transistors over the year. Two most common approaches was what it's typically called the current aperture vertical electron transistor and the trench MOSFET architecture. And in both of the technologies, our colleagues around the world have shown very promising performances with a breakdown voltage up to 1.5 kilovolt and a specific on resistance down to around 2 million centimeters square. So now, both of the approach relies on developing novel junction. For example, here we're showing a typical architecture of a vertical GaN transistor, where we have a p-type gallium nitride region that helps to form a junction between the n-type GaN and helps to confine the current. However, there is a fundamental problem with this junction-based approach, because the doping of the p-type doping of the gallium nitride has proven to be very challenging, and this device architecture requires regrowth, and regrowth is very expensive and sometimes technologically challenging. To overcome these two problems, our group have come out with a new approach where instead of developing a junction, we use geometric confinement and nanoscale patterning to control the carrier flow in a vertical transistor. So the beauty of this approach is we don't need any p-GaN and we don't need any regrowth. We can just take a simple epilayer structure with a n plus GaN, n minus GaN, and GaN heavily doped GaN substrate, and just pattern it and make our transistors. And that gives us a lot of design flexibilities where we can just control our process parameters and define various gate lengths, threshold voltage, and everything. So it opens up a whole new design space for high voltage, high power vertical transistor using gallium nitride. Using this approach, a few years ago, our group demonstrated 5 amps, 1200 volt vertical GaN power FinFET on bulk GaN substrates. These devices showed normally off performance with a threshold voltage of 1 volt, on-off ratio of 10 to the power 10, and 5 amps current in an area of 0.5 millimeter square die size. And not only that, if we look at also the switching performance of the devices, these devices show competitive performance among all the silicon carbide and silicon powered devices in terms of both current density, chip area, and the switching charge and switching speed. So now that was very promising start, and all of these demonstrated devices were made on a native gallium nitride substrate or freestanding bulk gallium nitride substrate. So now let me change the topic towards why we need GaN on silicon technology here. So one of the primary challenges with this vertical GaN FinFET on bulk gallium nitride substrate is the scaling down of the on resistance, which determines the switching loss. When we did analysis about the total resistance contribution of different components in the device, we found that 75% of our on resistance is coming from the substrate itself. Although the substrate is N plus gallium nitride, but the contribution of the 300 micron thick substrate is the major contributor to the whole R-on of the device. And the second most challenging part is the technological scaling of these devices. All these devices were made on, as I said, native gallium nitride or GaN on GaN substrate. These wafers are excellent because we can grow thick epi with very low defect density, which is important for vertical devices. But the wafer diameter is limited to 2 to 4 inch. And also the cost is significantly higher than any other, any traditional commercialized technology like silicon wafers. On the other hand, we have also option to develop this technology on traditional GaN on silicon platform. These wafers can come as large as 8-inch diameter, and the wafer cost is significantly lower. However, the defect density is a primary challenge in traditional GaN on silicon wafers. Also, it has been proven very challenging to develop thick epi layers on this traditional GaN on silicon wafers, which is required to support very high voltage devices. For example, here is a cross-section SEM from the literature. We're showing that the a typical GaN on silicon wafer where the dislocation density is very high and thickness is limited to avoid cracking. Also, due to the presence of insulating and defective buffer, the transport can be very challenging through this kind of structure. So to overcome these problems, we collaborated with a company, Chromis, where they have a patented technology, they call this QST engineered substrate technology. The key to this substrate technology is the substrate itself. So in this plot, we have the coefficient of thermal expansion for different substrate that can be used for gallium nitride. So the red one represents the CT for silicon, and here this curve is for the gallium nitride. As we can see, the coefficient of CT mismatch between silicon and GaN is really high, which causes the Epi to crack if we just grow directly on thick Epi on silicon. But these substrates from our collaborators, they use a aluminum nitride as the core, and the CT mismatch between the polycrystalline aluminum nitride and GaN is minimal, and which helps us to develop very thick Epi without cracking or high defect density. Here is an example of a 30 micron thick gallium nitride grown on this QST technology. And a better news is these wafers can be grown in 8 to 12-inch wafer scale. So that gives us immediate opportunity to scale up our device technologies and fabricate in a commercial fab. So motivated by this, we started developing our own technology on this QST GaN on silicon substrate a couple of years ago. This is our typical device flow, fabrication flow, which we have been doing in MIT.nano for many years now. So our device fabrication start with the etching of the gallium nitride fins, and then we define field oxide, which to manage the electric field, and we form the gates along the sidewall of these fins, and we etch the drain and mesa, and finally we do a planarization, silicon dioxide spacer, and pad metallization. I'll explain the important steps in next few slides. The first most important step in our fabrication technology is the fin formation. So for the fin formation, we deposit a silicon nickel hard mask through e-beam lithography and e-beam evaporation and do a dry etch to define the fin length, fin length and width. And after the dry etch, as we can see from this SEM image, there are a lot of sidewall damages due to from the dry etch. Since we want to have our channels across the sidewalls, it's very important to get rid of these damages and get a very smooth sidewall for our subsequent ALD deposition and gate metal patterning. So to do that, we align our fins with a specific crystal orientation that helps us to use a crystal plane selective wet etch, and that only etches the sidewalls significantly and a very low etch rate in the other crystal planes. And after a successful crystal plane selective wet etch and cleaning of the substrate, we get very nice smooth fins with this very excellent sidewalls. And once we have the fins, our next step is the gate patterning, where we deposit atomic layer with the atomic layer deposition with aluminum oxide across, wrapping around the fins, and we sputter gate metal on top of it. After that, we do a planarization and etch back to define the gate length. And finally, we remove our planarization dielectric, and then we have our fins with the gate oxide and gate metal. So in the first generation of devices, we were using a photoresist-based planarization process. The advantage of this photoresist-based planarization is it's etch selective because we can just etch it with an oxygen plasma. However, since it's a photoresist spin-on, it also depends on the process parameters and it's really hard to control. So recently, we have developed a PECVD silicon dioxide-based planarization technology, which is very robust and which also has, the etch chemistry is similar to our gate metal patterning chemistry. So we'll have to optimize that the etch process to get the perfect gate patterning process. As an intermediate solution, what we have pursued is an aluminum-based, wet etch-based gate patterning, where we use this TEOS PECVD silicon dioxide-based planarization Then we etch back the silicon dioxide with a CF4O2 chemistry. And once we have at the desired height for our gate length, we used a wet etch to selectively etch the aluminum from the sidewall and define our gate length. And finally, we use a subsequent CF1 oxygen dry etch to remove the planarization dielectric, which is in this case is silicon dioxide. And once we have our gate defined, the next step is the spacer oxide, which basically separates the gate metal from the source metal, which is on top. To do that, we again use a PECVD SiO2 solution, and we're using a TEOS precursor. And due to the use of TEOS precursor, the silicon dioxide actually grows conformally from the side walls. And once it keeps growing, it actually merges the front and nicely planarizes on top of the device. And after that, we can etch back. And once we expose the source region of the fins, we deposit our metal and finish the device fabrication. And this is a cross-section focus and beam image of one of our typical fabricated device, where we have the gallium nitride patterned fins, the gate metal on the side walls, the silicon dioxide spacer, and the source metal on top. So this is the spacer layer, which is separating the gate and source metal and avoid being shorted. And here we're showing our typical output characteristics of our GaN silicon FinFET fabricated on engineered substrate. We are reporting a current density of around 4 kiloamps per centimeter square if we normalize the current with respect to the fin and the spacing in between the fins. However, our current devices are limited by the source contact resistance, which we will need to improve by applying few techniques in future. If we consider the total current density flowing through each fin, it's actually very high. It's more than 30 kiloamps per centimeter square. So although currently the normalized current density over the active area is about 4 kiloamps per centimeter square, in future we can make the fin density higher and even achieve a higher current rating from these devices. So this current density is showing a potential for further scaling of the current rating of these devices. So now if we want to benchmark where our devices stand in terms of the other GaN on silicon vertical transistor in literature, here on the right-hand side on the plot, we're showing the different technologies that our colleagues have published around the world. And in our first generation of fabricated devices, our current density is much higher than any other GaN on silicon vertical transistor present in the literature. This is a very promising result given that we have not optimized the technologies yet, and that also encourages us to pursue this direction even further. So now I'll talk about a novel substrate replacement technology that we have developed to further push the limits of these FinFETs on silicon substrate. So in the first generation of devices, we use a quasi-vertical architecture for devices where our drain layer was not exactly in the bottom of the device. We still have the QS3 substrate remaining and the buffer layer that used for growth. And we etch down the drain layer and put the source layer on top of this from here so that we can probe from the top. But that's not that's not possible if you want to do a really high voltage devices where the thickness of the drift region would be tens of microns. We need to develop a technology where we can, the drain metal can be at the bottom of the substrate instead of from the top. So what we want to develop in the next generation is a fully vertical architecture where we'll have our source on the top, gates on the sidewall, and the drain at the bottom. And if we want to achieve a 1200-fold rating, from our experience and calculation, we know that we need about 10 micrometer thick drift. And to demonstrate this second generation device, we have to develop a substrate removal and replacement technology. We have to replace the substrate because for the mechanical stability. And since the substrate resistance was the 75% of the total on resistance of the FinFET, if we remove the substrate completely, it will also help us with the on resistance of the device and the thermal management because of the ultra thin nature and the conductive electroplated copper on the backside of the device. Now, the substrate removal is very challenging because of the complicated structure of the this engineered substrate itself. If you look at the substrate, once we are fabricating the device, and this is the substrate underneath, if you look closely at the substrate underneath the N+ gallium nitride drain has many layers, such as GaN buffer layers, silicon 111, the engineered layers, and the polycrystalline aluminum nitride core. So we developed a process where we first use a temporary bonding to attach the sample upside down on a carrier wafer. Then we grind the polycrystalline aluminum nitride from 700 micron to 50 to 100 micron thin, and we use a hot KOH wet edge to remove the rest of the gallium, aluminum nitride. And then we use a combination of dry and wet edge to remove the engineered layers. And we dry edge the silicon 111 and also time dry edge the GaN buffer layer to stop on the N+ drain. So this is one of the example of when we were developing the process. Here on the left, we have this sapphire carrier used for this substrate removal process, and this temporary bonding material HT1011. And this is after complete substrate removal, we can see that it's ultra thin gallium nitride, which is about 10 micron thick, remaining on the substrate. And since it's a wide bandgap material, it's completely transparent, as we can see on the right-hand side. So now that we have developed the substrate removal technology, the next step is to replace it so that we can debond the carrier and have a freestanding device. So to do that, we start with the first our drain side contact, which is typically we use Thai aluminum. We sputter the drain contact on top of the N+ GaN, and then we use a diffusion barrier titanium nitride. And for electroplating, we deposit copper as the seed layer, and we electroplate 50 to 100 micron copper. And finally, we debond through the temporary bonding material, and we have our freestanding devices. So before going into the FinFET fabrication, we developed the process in a simpler structure on diode devices. So the diode structure after fabrication and before substrate removal looks like the one I'm showing here on the left. So we have nickel gold nickel Schottky contact on the front side. Then we have the drift region, which is about 10 micron thick, and the N+ GaN bottom layer, and a QST substrate. And once we remove everything and replace the substrate with electroplated copper, this is one of our finished substrate, how it looks like. So here we have a freestanding gallium nitride Schottky diodes fabricated on a 50 micron copper. And if you zoom in, we can see the diode patterns all over the surface. And as it happened yesterday, we measured our first fully vertical Schottky diode after substrate replacement in the lab. And this is the typical IV characteristics of the fabricated Schottky diode of a freestanding freestanding gallium nitride from a QST substrate on 50 micron electroplated copper. We'll need to improve the device characteristics further by advanced engineering, but this is a promising start for our fully vertical devices. So our next step would be to fabricate fully vertical FinFET on this QST substrate. So we have fabricated the FinFETs on the substrate, and now we are working on the substrate removal. And hopefully in near future, we'll be able to characterize and demonstrate the first generation of the fully vertical devices with the replaced substrate. So this is a very promising development that we are working on our lab, but I would also like to point out that GaN has been the heterogeneous integration of GaN on silicon has been out there for a while. For example, our group in 2012 demonstrated lateral GaN hems on a silicon substrate and a side-by-side technology over a 6-inch wafer. And recently, Intel took it to the next level, and they demonstrated a GaN on silicon heterogeneous integration of a 12-inch wafer. And these devices are being considered for power and RF delivery and a lot of different applications that wide bandgap and high mobility materials can enable. So our technology is along the same line where we're trying to develop on silicon substrate that can be transferred directly into commercial fab and enable many new applications in a much wider voltage range and the power capability. in summary, today I have shown that our first demonstration of quasi-vertical GaN-on-silicon FinFET on engineered QST substrate, and our first generation of devices has shown promising performance and record current density among all the GaN-on-silicon vertical transistor. We have developed a novel substrate replacement technology that promises superior thermal management and better switching loss. And finally, we are fresh from the lab. We are first fully vertical Schottky diode with replaced substrate. At this point, I would like, this is the most important slide of my talk. I would like to acknowledge all the people. Without their help, the work hadn't been possible. And the most important people in this slides are the graduate students who are spending all their days and nights in the lab, Josh and John, who made this technology possible, and our funding sources, Samsung, ARPA-E, and DARPA, with their generous support, our research has been possible here. And a lot of people from our collaborating Chromis, Brewer Science, and different groups from MIT, and of course, all the staff and the from the MIT.nano. Without their help, nothing would have been possible. And at this point, I would like to thank the organizer for inviting me, and I'd be happy to take any question.
Ahmad, thank you so much for a great talk. If you have any questions for Ahmad, and I'm sure there are many, please do feel free to either raise your hand, and myself or Charisse will call upon you. And secondly, make sure you indeed send us some chat questions if that's better for you. Either way, we're going to try to call on you and relate your question to Ahmad. Yes, we have a question from Youngjun Kim.
Yeah, thank you. Thank you for the nice presentation. Just one quick question. So gallium nitride on the QST, that structure, you have deposited III-Nitride before copper electroplating, but usually in semi area, tantalum nitride or tantalum is regarded as very good copper diffusion barrier. Any particular reason why using III-Nitride? And then also at a very high temperature, I don't know if III-Nitride can prevent copper diffusion into transistor area. Yeah, the temperature is quite different from the usual semi, right?
Yeah.
For this gallium nitride.
Yeah, so excellent question. Yeah, I think that, as this tantalum nitride is the standard diffusion barrier for that industry has been using for a while. I think we're still working on developing a tantalum nitride diffusion barrier right now. The tools we're using, currently we have developed a recipe for the titanium nitride, and that works well for our purposes for now, but in future we plan to expand it to the tantalum nitride. And regarding the thermal budget, well, actually our thermal budget is limited by the stability of the dielectric on the front end of the device. So we cannot, from our experience so far, we saw that we cannot go beyond 500 Celsius with the current gate technology that we have. So in this current generation of devices, our thermal budget will be limited to 500 degrees Celsius anyways. So that shouldn't be a problem for now. But of course, in future, we'll have to use tantalum nitride and a better other technologies to make it compatible with other technologies. Yeah. Thank you for the question.
Thank you. So may I give one more question?
Of course, please go ahead.
Yeah, then your another applications, the vertical structure, gallium nitride on silicon platform. So if you compare this one, for example, gallium nitride and silicon carbide, which is also vertical current transportation. So your structure has any benefit over that the gallium nitride and silicon, which is has inherent benefit, right?
I think the inherent benefit comes from the scalability of this. The substrate itself is now already in the 8-inch, and it can go into the 12-inch. I mean, they're working on to develop a 12-inch substrate soon. I think the primary benefit is coming from that fact that we can immediately scale up for the commercial fabrication in a very large scale device demonstration.
In terms of cost, do you mean?
Yeah, in terms of cost. And also, I think they have shown that they can grow 30 micron thick epi without cracking. So if in future, if you want to expand the voltage handling capability of these devices, this technology can be proved really advantageous.
Okay, thank you.
All right. Any additional questions, please do raise your hands and we will call upon you, or you can send them in a chat to everyone. I'll do my best to represent your question most appropriately. Ahmad, your technology is remarkable, right? I mean, the high power electronics, the high kind of currents you're able to achieve. It is also relatively bulky, let's say, in comparison to a typical silicon high node transistor. So the question in my mind would be, what is the ultimate speed you think you could achieve with the technology as it's done right now, or maybe as it will be done in the future? And what is a needed frequency of response, given the fact that many of these transistors would be used for power electronics that do not require extremely high frequencies? Wonder if you could comment on that, the speed of response.
Yeah, thank you. Excellent question. So you are right. It's a very bulky. If you look into the speed of the power electronics these days, we are still in the range of kilohertz to, we're really pushing towards the megahertz frequency of response in the power electronics. So that's where I think the high mobility of the gallium nitride and other materials comes into play. So I think with these technologies, we can, when we go to the high mobility materials, we can go to the higher frequency, and the higher frequency also advantageous for power electronics because it helps us to scale down the size of the passive components such as capacitor, inductor, and it also helps with the form factor of the whole system. For example, I think in the very beginning. So for example, here the whole module that Tesla and STMicroelectronics developing on silicon carbide, it's also already showing a significant reduction of the form factor compared to silicon technologies, just because the superior transport and the mobility in the material itself. But I think getting a megahertz power electronics would be amazing at high voltage level for now. And I think if you talk about high frequency, high power, our group is also working on these transistors. Also, we are trying to optimize for high frequency, high power, where we are targeting 30 gigahertz to higher ranges, where we can develop really high power for different level of application, not exactly for this kind of our traditional power electronics. So by changing the device architecture, we can go for traditional higher power electronics with higher power capability up to megahertz, probably beyond. But if we change the architecture and do some device engineering, can push to high power, high electronics to even tens of gigahertz.
Yeah, of course, there's always a fundamental power bandwidth product limit, and indeed, it would be intriguing to consider it. My very last question, as we are running out of time, what is the biggest challenge now from perspective of the next step? Is that series resistance of the source contact, or is it the capacitance of the very large gate electrodes that you might be using? Is there the next obvious thing for you to tackle to make these devices even better?
Yeah, I think as you said, the immediate challenge that we're really looking for to solve with the source contact resistance. So right now, our as I showed in my IV, that is not particularly great, but we know that if we can add some rapid thermal annealing without degrading the gate stack, or maybe some other advanced technology, that can really help to improve the performance of the device. I think that's the primary direction what we are looking right now to improve the on resistance by improving the source contacts.
All right. Well, Ahmad, thank you so much for giving us a fantastic talk. I did receive a question in the chat on where will the talk be available. It will be available on MIT.nano website, MIT.nano.mit.edu. You can go under the events and seminars and Nano Explorations is among there, and all of the previous talks indeed all of previous talks we received permission to post, and that's most of them, are available there for your perusal. This talk will be available within the next couple of weeks, and you'll have a chance to enjoy Ahmad's great talk one more time, if you wish to do so. At this point, I would like to conclude by just simply reminding you of the upcoming Nano Explorations talk. It is going to happen 2 weeks from now, March 16th, 11 a.m. Eastern Standard Time. Jules Stewart will tell us about integrated photonics and electronics for chip-scale quantum control of trapped ions. I hope you'll be able to join us then. Thank you again for being with us today. Take care.